If the idea that millions of tons of ice are already committed to melting, locked in, irreversible, happening regardless of anything humanity does from this moment forward, has you as focused as it has me, hit like and subscribe to Signal Watch right now so you don't miss a single update as this story develops. Drop a comment below and tell us where you're watching from, what time it is there, and this question. If your nearest coastline moved 10 kilometers inland within your lifetime, what would be the first thing in your community that disappears underwater? Think about it and let us know below. And if you want to help this community keep growing, share this video on X, Facebook, Reddit, or even just your group chats. You're the reason we can keep chasing stories like this. So thank you for having our back. Now, ice that is structurally attached to the Greenland ice sheet but has already lost its accumulation source, dead on its feet, melting from below by warm Atlantic water that has no business being where it is. Subglacial rivers carving channels through the base of glaciers that took 100,000 years to build. A marine ice sheet instability mechanism that, once triggered, the physics says cannot be stopped. And a sea level commitment number that glaciologists are publishing in peer-reviewed journals that has not made it into a single coastal infrastructure planning document anywhere on the planet. Now, settle in and let's get into it. There is a category of ice on Greenland that has no future. It is still frozen. It is still physically attached to the glaciers and ice sheet that cover 80% of the world's largest island. It is not yet melted, but the process that sustained it, the accumulation of new snow on the upper reaches of the ice sheet that feeds downward, replenishing the lower glacial margins, has broken down to the point where the lower ice has been effectively cut off from its supply. It is receiving no new material. It is losing mass at its edges and base to a warming ocean and a warming atmosphere. It is, in the terminology that glaciologist Jason Box at the National Geological Survey of Denmark and Greenland, known by the acronym GEOS, introduced to the peer-reviewed literature and to public communication, zombie ice. The term is not casual. It encodes a specific physical reality. Zombie ice is ice that is structurally present but functionally disconnected from the replenishment system that would allow it to persist. It is doomed by the imbalance between accumulation and ablation, the addition and removal of mass that has already been set in motion by the warming of the Arctic at a rate roughly 4 times the global average. When Box and colleagues published their analysis in Nature Climate Change in 2022, the conclusion was stated with the kind of directness that is unusual in peer-reviewed science. At least 365 millimeters of global sea level rise is already locked in from Greenland zombie ice alone, not projected under a worst-case scenario, not contingent on future emissions trajectories, locked in, committed, regardless of what humanity does from the publication date forward. 365 millimeters. That number deserves to sit in silence for a moment before we move on from it. 365 millimeters is approximately the height from the floor to the seat of a standard chair. It is the permanent elevation of mean sea level along every coastline on Earth. The Atlantic, the Pacific, the Indian Ocean, the Mediterranean, the Gulf of Mexico, by an amount that will interact with every tide, every storm surge, every king tide event for as long as the ocean exists in its current configuration. There is no scenario in which that rise does not occur. The decision was made by the physics, not by any future policy. The ice that will produce it is already standing on Greenland, already cut off from its source, already dying in place. And that is the minimum. That is the committed rise from zombie ice alone, without accounting for the dynamic processes, the marine ice sheet instabilities, the basal melt acceleration, the subglacial hydrology changes, the ice cliff mechanics, that this investigation is going to examine in detail. Because zombie ice is the floor. The physics says the ceiling is somewhere above it that the models have not yet agreed upon. But every time the models are updated with better observational data, the ceiling goes up, not down. The story of how Greenland arrived at this point requires understanding what Greenland actually is, not as a geographic curiosity at the margin of a map, but as a physical system of staggering scale whose behavior over the next century will determine the habitability of coastlines, on which approximately 1 billion people currently live. The Greenland ice sheet contains approximately 2,900,000 cubic kilometers of ice. If that volume were spread uniformly across the continental United States, it would produce an ice sheet approximately 300 meters deep, roughly the height of the Eiffel Tower, blanketing the entire country. Its sea level equivalent is approximately 7.2 meters of global mean sea level rise if it melted entirely. 7.2 meters is the height of a two-story building above the current shoreline at every beach on Earth. It is the permanent relocation of the coastline of the eastern United States to somewhere in the vicinity of Interstate 95 in many areas. It is the complete, permanent inundation of the Nile Delta, the Mekong Delta, the Ganges-Brahmaputra Delta, and the majority of the Netherlands as it currently exists. The complete melting of Greenland is not the scenario of the next decade. It is the scenario of centuries under any realistic trajectory. But zombie ice is not the complete melting. It is the first, already committed installment of a process that the physics says is now underway and cannot be recalled. To understand why zombie ice is irreversible, you need to understand the maintenance system of an ice sheet. The continuous cycle of accumulation, internal flow, and ablation that keeps a body of ice in dynamic equilibrium against the constant thermodynamic pressure to melt. The Greenland ice sheet is not a static block of frozen water sitting inertly on bedrock. It is a dynamic system in continuous motion, a slow, cold river of ice flowing outward from a central dome toward a coastal fringe of outlet glaciers and ice shelves. Snow falls on the interior at the high elevation dome that reaches approximately 3,200 meters above sea level at Summit Station, the research installation in central Greenland. That snow compresses under the weight of subsequent snowfall, transitioning first into firn, a granular intermediate stage between fresh snow and solid glacial ice, and then into the dense blue-tinted glacial ice visible in calving fronts and crevasse walls. The ice, under the immense pressure of its own accumulated weight, deforms and flows outward from the central accumulation zones toward the margins, where it either calves as icebergs into the ocean or melts at the surface during warm seasons and runs off as meltwater rivers and streams. The flow rate of this ice varies enormously across the ice sheet. At Summit, the ice moves at millimeters per year, barely measurable without precision instruments. At the fast-moving outlet glaciers that drain the ice sheet into the ocean through narrow coastal fjords, the flow reaches extraordinary velocities. Jakobshavn Isbrae, Cermak Kujalek in Greenlandic, translating roughly to the glacier that moves fast, is typically cited as one of the fastest moving glaciers on Earth. Its flow velocities have reached 40 to 46 meters per day in peak measured periods. That velocity means the glacier is advancing the length of a standard football field every 2 to 3 days, a pace that reflects a system under severe and accelerating dynamic stress. In a balanced ice sheet, one in the dynamic equilibrium that characterized Greenland through most of the Holocene, and certainly throughout human recorded history, the ice added by snowfall at the interior precisely equals the ice lost by calving and surface melt at the margins. The ice sheet neither grows nor shrinks. The concept of mass balancing, the difference between accumulation and ablation measured in gigatons or billions of tons per year, is the fundamental metric for assessing ice sheet health. The Greenland ice sheet has been in sustained, accelerating negative mass balance, losing substantially more than it gains since at least the 1990s. The IMBY Consortium, the ice sheet mass balance inter-comparison exercise, coordinated by Andrew Shepard at the University of Leeds and involving more than 80 scientists working with data from multiple satellite measurement systems, established through their synthesis that Greenland lost approximately 3.8 trillion tons of ice between 1992 and 2020. 3.8 trillion tons. Every ton of that ice is now in the ocean, distributed as a thin but permanent addition to global mean sea level. The mass loss rate within that period has not been constant. It has accelerated. The average annual loss from 1992 to 2000 was approximately 34 billion tons per year. From 2000 to 2012, it averaged approximately 215 billion tons per year. From 2012 to 2020, it averaged approximately 280 billion tons per year, more than 8 times the rate of the 1990s. The trend line in the IMBY data does not flatten. It does not plateau. It rises. Zombie ice is the surface manifestation of this accelerating negative mass balance as expressed at the glacier margins. When the accumulation area of a glacier, the upper elevation zone where annual snowfall exceeds annual melt and the mass balance is positive, shrinks due to warming temperatures that push the equilibrium line altitude higher, the lower reaches of the glacier that depend on that accumulation for their replenishment are progressively cut off. The accumulation area ratio, the fraction of the total glacier area receiving positive mass balance, falls below the threshold needed to sustain the lower margins. Those lower margins continue to exist as frozen water. They are still ice. They are still attached to the glacier, but they are no longer being refreshed by downward flow from the interior. They are drawing down a finite reserve, and the reserve has no incoming supply line. Box's calculation asks precisely, given the current accumulation area ratios across all of Greenland's glaciated drainage basins, what is the minimum volume of ice that is committed to melt even under a scenario of instantaneous cessation of all further warming? The answer was 365 millimeters of sea level equivalent, 1 year's worth of sea level rise at current rates, locked in before the climate does 1 more degree of warming. The zombie ice calculation is, in a specific and important sense, the conservative lower bound. It accounts for the surface process imbalance, the disruption of the accumulation-ablation equilibrium by atmospheric warming. What it does not fully integrate is the attack from below. And the attack from below is where some of the most alarming measurements in the current Greenland observational record are emerging. Beneath Greenland's glaciers, where ice contacts the ocean at the submarine faces of glacier fronts and floating ice tongues, a process is occurring that the scientific community has radically revised upward in its intensity estimates over the past decade. Basal melt, the melting of ice from its ocean-facing underside by seawater that is warmer than the freezing point of ice, is not a new phenomenon. What is new is the temperature of the water doing the melting, the depths to which that warm water is intruding, and the rate at which those intrusions are driving ice loss. The Atlantic water, a warm, salty water mass that circulates through the subpolar North Atlantic at intermediate depths, typically between roughly 200 and 800 meters below the surface, has been warming. The broader Atlantic warming pattern, connected to the sea surface temperature anomalies documented in the AMOC investigation, is not confined to the surface layer. Analyses of Argo float profiles, the global network of autonomous oceanographic sensors that measure temperature and salinity from the surface to 2,000 meters, show that Atlantic water reaching the mouths of Greenland's fjords has warmed by approximately 1 to 2 degrees Celsius over the past several decades, with the most significant warming in the deep layers that directly contact glacier bases. Fiamma Stranio at the Scripps Institution of Oceanography deployed oceanographic instruments inside several of Greenland's major fjords, including Sermelik Fjord, which drains Helheim Glacier on the southeast coast, and Ilulissat Icefjord, which drains Jakobshavn Isbre. Her measurements, requiring specialized fieldwork in some of the most logistically challenging ocean environments on the planet, established the temperature and salinity structure of the water in direct contact with the glacier fronts. Atlantic water reaching some glacier bases had temperatures of 1 to 4 degrees Celsius above the pressure melting point of ice. Not atmospheric temperature, ocean temperature, in direct, continuous contact with the glacier's submerged face. 1 degree Celsius above ice's melting point, applied continuously over a large submerged area, melts ice at a rate that may seem modest in a single day, but is relentless in aggregate. 4 degrees above melting, applied to the submarine face of a glacier, calving into a fjord through which Atlantic water circulates continuously, produces submarine melt rates that Eric Rignow's team at NASA's Jet Propulsion Laboratory quantified in their landmark 2019 science publication. Their analysis, using ocean current measurements and detailed fjord geometry data, established that submarine melt at Greenland's glacier fronts had been underestimated by factors of 7 to 8 in previous assessments. 7 to 8 times the previously assumed rate, not a marginal correction, a fundamental revision to the understanding of how fast Greenland is losing mass through ocean contact. When you revise the basal melt rate upward by a factor of 7 to 8, every model that was calibrated on the previous estimates becomes, in that specific dimension, wrong by that factor. The ice sheet's response time to ocean warming is 7 to 8 times more sensitive than the previous generation of models assumed. The retreat timelines accelerate. The committed sea level contributions increase. The risk assessment framework requires reconstruction from its ocean forcing inputs upward. The ocean attack on glacier fronts is visible in principle, accessible to direct measurement with oceanographic instruments deployed in fjords. The attack from directly beneath the ice sheet, the subglacial hydrology that is reshaping the base of Greenland's glaciers from the inside, is far harder to observe and has only become tractable as a research question with the advent of airborne radar that can penetrate thousands of meters of ice to map the geometry of the bed below. Beneath the Greenland ice sheet, between the base of the ice and the bedrock that underlies it, a hydrological system of enormous scale and complexity operates invisibly. Meltwater generated at the ice sheet surface from direct solar and atmospheric warming during the summer melt season does not simply run off the ice sheet's edges and into the ocean at the margins. A substantial portion finds its way to the ice sheet bed through moulins, vertical shafts that form where surface meltwater exploits pre-existing crevasses and the thermal erosion of flowing water to penetrate the full ice thickness. A moulin can be several meters in diameter and can descend hundreds to thousands of meters through glacial ice, essentially river dropping vertically through the glacier to the bed below, carrying thermal energy and mechanical erosive power into contact with the ice bedrock interface. At the bed, this water behaves very differently depending on the drainage geometry it encounters. If the bed is characterized by abundant small pores and distributed pathways, the distributed drainage mode, water films across wide areas, lubricating the ice bedrock interface broadly. This lubrication reduces basal friction. Less friction means the glacier slides faster over its bed. Ice velocities increase. More ice moves toward the ocean margin. In the channelized drainage mode, meltwater organizes into efficient conduits, carved into the ice or the bedrock, that route water rapidly to the glacier margins without the broad lubrication effect. Channelized drainage evacuates water efficiently and actually reduces glacier velocity compared to the distributed mode. The transition between distributed and channelized drainage is seasonal and responds to the rate of meltwater input. Early in the melt season, spring, when meltwater first reaches the bed, distributed drainage prevails and glacier velocities spike. As summer progresses and meltwater input remains high, efficient channels develop and velocities moderate. This seasonal velocity cycle has been documented by Ian Bartholomew at the University of Edinburgh and colleagues using GPS measurements on western Greenland glaciers. Their data shows spring accelerations of 20 to 50% above winter baseline for periods of several weeks, measurable from satellites and confirmed by ground instruments. As melt seasons lengthen and intensify, the spring acceleration phase becomes longer. Glaciers spend more of the year in the high-velocity distributed drainage mode. The net annual delivery of ice to the ocean margins increases. But this velocity dynamic is, in a specific sense, the secondary concern in the subglacial hydrology picture. The primary concern is what sustained subglacial water flow does to the structural integrity of the ice sheet base over timescales longer than a single melt season. Water flowing at the base of an ice sheet, warm relative to the surrounding ice, carrying suspended sediment, moving under hydraulic head gradients driven by ice surface slope, erodes, and reshapes the subglacial terrain. In regions where the bed topography creates over-deepened basins, areas where the bed is below sea level and slopes downward into the interior. Subglacial water can become trapped and accumulated into subglacial lakes. More than 50 subglacial lakes have been identified beneath the Greenland ice sheet using ice-penetrating radar and surface altimetry data from IceSat and IceSat-2, the NASA Ice, Cloud, and Land Elevation satellite missions. These lakes periodically drain, releasing large pulses of subglacial water that temporarily accelerate glacier flow. The thermal energy that subglacial water carries, the heat of the water itself, and the latent heat released when ice at the pressure melting point is in contact with water slightly above that temperature, continuously erodes the ice base. Over decades, this thermal erosion widens subglacial channels, deepens over-deepened basins, and progressively weakens the structural architecture of the lower ice sheet. The ice that is structurally compromised at its base is the same ice that the ocean water will encounter when it penetrates further up the fjords and beneath the floating ice tongues. The subglacial and oceanic attacks are not independent. They are preparing the same ice for the same fate from two directions simultaneously. There is a physical mechanism in glaciology whose name, in the context of this investigation, carries a very specific weight. It is called marine ice sheet instability, abbreviated MISI. It was first described theoretically by Johannes Wertmann at Northwestern University in 1974. It has been elaborated, modeled, and observationally tested in the decades since, and it represents the transition from the gradual, measurable, alarming, but manageable ice loss we have been tracking through the first 4 parts of this investigation to the self-reinforcing, unstoppable, committed dynamic retreat that defines the ceiling above the zombie ice floor. The physical principle is geometrically elegant and deeply consequential. Marine ice sheet instability applies specifically to ice sheets where the bed beneath the ice, the solid surface on which the ice rests, slopes downward going inland from the ice margin. This geometry is called a retrograde slope, and it is found in significant portions of Greenland's marine-based outlet glacier sectors, as revealed by the BedMap Greenland compilation of ice-penetrating radar measurements. When the grounding line, the boundary between ice that is resting on the bed and ice that is floating on the ocean, retreats inland along a retrograde slope, it retreats into deeper water. Deeper water means a taller submerged ice face at the calving front. A taller submerged ice face means greater contact area with the warm Atlantic water driving submarine melt. Greater submarine melt means faster calving and faster ice removal. Faster ice removal means the grounding line retreats further inland into still deeper water, into a still taller ice face, into still faster melt. Each step of the retreat creates the conditions for the next step. The feedback is positive and self-reinforcing. There is no physical restoring force that increases with retreat distance and eventually arrests the process. Once a grounding line on a retrograde slope retreats beyond a critical threshold, the exact position of which depends on the specific geometry and the rate of external forcing. The retreat is theoretically committed. It continues until the grounding line reaches a region where the bed slope reverses, where the bed rises from the interior toward the coast, allowing the ice to stabilize at a new grounding line position, potentially many kilometers or tens of kilometers further inland. At Jakobshavn Isbra, the grounding line has retreated approximately 40 kilometers since the late 1990s. The bed beneath the glacier in the retreated region deepened substantially going inland, precisely the retrograde geometry that MISI acts upon. Ian Jowan at the University of Washington's Applied Physics Laboratory, whose observational work on Jakobshavn and other fast-moving Greenland glaciers has provided some of the most important data in the field, has characterized Jakobshavn as already in an unstable retreat mode, consistent with marine instability dynamics. This is not a future projection. It is the current observational state of the glacier, the volume of ice that could be mobilized by marine instability processes in Greenland's retrograde sloped marine sectors, the ice that is not in Box's zombie ice calculation, but that Misi dynamics could commit to the ocean as the grounding lines continue their retreat, is substantial and difficult to bound tightly with current models. But it is measurably more than the zombie ice floor. How much more depends on how quickly the instability processes operate, which is the central quantitative uncertainty in the current literature. The physics says the process is in motion. The models disagree on the speed. The story of Greenland's accelerating ice loss is not told only through models and projections. It is told, with increasing precision and redundancy, by one of the most comprehensive remote sensing campaigns in the history of Earth observation. A suite of independent satellite and airborne measurement systems, observing the same ice sheet from different physical perspectives and arriving at consistent, mutually reinforcing conclusions. The GRACE-FO satellite mission, the Gravity Recovery and Climate Experiment follow-on, operated jointly by NASA and the German Research Center for Geosciences, flies two identical satellites in the same polar orbit, separated by approximately 220 kilometers. The microwave ranging system between the two satellites measures their separation to an accuracy of approximately 1 micron, roughly 1/50th the diameter of a human hair, when mass is redistributed on Earth's surface. When the Greenland ice sheet loses ice and that water flows into the ocean, the gravitational field of the ice sheet weakens, and the slight change in gravitational pull on the trailing satellite alters the separation distance in a way that can be precisely measured and inverted to produce a monthly map of mass change. The GRACE-FO data for Greenland shows a mass loss rate of approximately 250 to 300 billion tons per year over the most recent measurement periods, consistent with the longer GRACE record extending back to 2002. The monthly resolution of the GRACE-FO product allows tracking of the seasonal cycle, the spring and summer peak of surface melt and runoff, the winter quiescence during which accumulation partially offsets the annual deficit, alongside the long-term trend that is unmistakably and consistently negative. Every year in the GRACE-FO record adds to the cumulative mass deficit. There are no years of substantial recovery. The trend is one direction. The European Space Agency's Cryosat-2 satellite, carrying a radar altimeter specifically engineered to measure the surface elevation of ice sheets and sea ice with centimeter-level precision from orbit, provides a complementary measurement. Where GRACE-FO measures total mass, Cryosat-2 measures surface height, ice sheet thinning, whether from surface melt, reduced snowfall accumulation, or the dynamic drawdown of ice through accelerated glacier flow, appears as a lowering of the surface elevation, detectable in repeat altimetry measurements. The combination of the two systems allows researchers to separate the surface melt component from the dynamic component of mass loss, a separation with important implications for understanding which processes are driving the acceleration. When the IMBY team synthesized GRACE-FO, Cryosat-2, and input-output data, where input is snowfall accumulation measured by atmospheric reanalysis, and output is ice flux across the grounding line measured by INSAR velocity multiplied by ice thickness from radar sounding. The three independent approaches agreed. Mass loss has accelerated. The dynamic component, ice flowing faster toward the margins and calving into the ocean, accounts for a growing fraction of total loss, rising from roughly 30% in the 1990s to approximately 40 to 50% in recent periods. The growth of the dynamic fraction is the observational signature of the marine instability processes operating at the glacier level. The ice is not just melting in place, it is moving faster toward the ocean because the dynamics of its marine margins have been destabilized. The Copernicus Sentinel-1 constellation, operated by the European Space Agency as part of the European Union's Earth observation program, provides the most comprehensive and current ice velocity data available through synthetic aperture radar interferometry. The 12-day repeat cycle of Sentinel-1's orbital configuration allows the derivation of ice surface velocity maps across the full Greenland ice sheet at spatial resolutions of tens to hundreds of meters. The NASA Measures program, Making Earth System, data records for use in research environments, has compiled these velocity maps into time series that reveal the multi-year acceleration of specific outlet glaciers with clarity unavailable from any previous satellite system. The velocity record for Jakobshavn-Isbra from Measures data shows the glacier approximately doubling its flow speed between the mid-1990s and the early 2010s. That doubling is the velocity signature of Missy dynamics in operation. The glacier responding to its retreating grounding line on a retrograde slope by accelerating the ice flux to the calving front. There is a specific scientific concept that sits at the center of the most consequential question this investigation raises. Not how much ice Greenland is losing, which is measured and documented, but whether the current rate of loss and the current state of the ice sheet's dynamic margins represent a threshold crossing from which recovery is impossible at any timescale meaningful to human civilization. The tipping point concept, as applied to Earth system components, was systematized with particular influence by Timothy Lenton at the University of Exeter and colleagues in their landmark 2018 Nature paper. Lenton's framework identified a set of large-scale components of the Earth system: the Amazon rainforest, the Atlantic meridional overturning circulation, the West Antarctic ice sheet, the Greenland ice sheet, among others, that exhibit threshold behavior, where gradual changes in forcing can produce rapid, self-reinforcing transitions to qualitatively different states. These components were called tipping elements, and their potential interactions, the possibility that one tipping element, crossing its threshold, could force another element toward its own threshold through teleconnections, were described as tipping cascades. The Greenland ice sheet's estimated tipping threshold, the global mean temperature above which committed full or partial ice sheet loss becomes irreversible on multimillennial timescales, was assessed by Lenton and colleagues at approximately 1.5 to 2 degrees Celsius above the pre-industrial baseline. That range is not coincidentally identical to the Paris Agreement's temperature targets. The Paris targets were informed by the same scientific literature that Lenton systematized. They represent the boundary within which the largest Earth system, tipping elements, are estimated to remain below their critical thresholds. Global mean temperature has reached approximately 1.1 to 1.2 degrees Celsius above pre-industrial as a multi-year average. The calendar year 2023 exceeded 1.5 degrees above pre-industrial for the first time as an annual average by multiple measurement systems. The year 2024 continued in a similar regime. Whether these exceedances represent a sustained crossing of the Greenland tipping threshold or a temporary fluctuation that the system can recover from is one of the most consequential open questions in contemporary Earth system science. Jonathan Bamber at the University of Bristol has assessed the probability of Greenland ice sheet contributions to sea level rise across a full range of emissions and temperature scenarios using expert elicitation, a method of formally synthesizing the judgment of the relevant scientific community when model-based projections carry large uncertainties. His work, published in the Proceedings of the National Academy of Sciences in 2019, established that under high-end warming scenarios, structured expert judgment assigned meaningful probability to Greenland, contributing multiple meters of sea level rise by 2100, a range substantially exceeding the IPCC's central estimates. The tail of the distribution was fatter than the model ensembles alone suggested. The honest statement of where the tipping point science stands is this: the processes that could drive Greenland past a committed large-scale loss threshold are operating and observable. The temperature forcing that is estimated to trigger that threshold has been transiently approached. Whether the threshold has been crossed, whether the ice sheet is now in a regime from which it cannot recover even with aggressive emissions reduction, is a question the current observational and modeling tools cannot definitively answer. The uncertainty is not symmetric. The processes that drive higher-end outcomes are the ones models have historically underrepresented. The physical evidence trends toward greater concern, not lesser. Marine ice sheet. Instability is not the only self-reinforcing physical process that glaciologists have identified in Greenland's marine-based ice system. It operates in context with a second mechanism, one that entered the mainstream ice sheet modeling literature through the work of David Pollard at Penn State University and Robert DeCanto at the University of Massachusetts Amherst, whose 2016 Nature paper produced results that the scientific community has been actively engaging with ever since. Marine ice cliff instability, MECI, is a mechanically driven collapse process that becomes relevant when retreating. Glaciers expose very tall vertical ice cliffs at the calving front, a geometry that can emerge when grounding line retreat on a retrograde slope removes the floating ice shelf that previously slowed calving and exposes the full ice thickness directly to the ocean. The structural mechanics are not subtle. Ice has finite compressive and tensile strength, a vertical column of ice above approximately 80 to 100 meters. The height at which the stresses in the ice near the base of the cliff exceed the material strength is mechanically unstable. It will fail. The failure mode is not the controlled calving of tabular icebergs from a floating shelf, where buoyancy provides partial mechanical support. It is the brittle collapse of a freestanding ice cliff whose lower portion cannot support the weight above it. Large sections of the exposed ice face fracture and fall into the ocean in rapid succession, retreating the cliff face backward and exposing new ice to the same instability. When MECI is combined with MISI, when marine instability retreats the grounding line into deep water where ice cliffs exceed the stability threshold, and those cliffs then fail rapidly and drive still faster, grounding line retreat into still deeper water. The cascade is potentially faster than either mechanism alone. Pollard and DeCanto's modeling results, incorporating both mechanisms, produce substantially higher sea level rise projections than models with neither, raising end-of-century estimates by meters under high warming scenarios. The subsequent scientific response was extensive and genuine. Tamsin Edwards at King's College London and a broad author team published a 2019 Nature paper using an emulator approach to constrain ice sheet model parameters against paleoclimate sea level records from past warm periods when temperatures were similar to current projections. Their analysis found that the most extreme MECI projections were not consistent with the geological evidence. Either the mechanism operated more slowly in past warm periods than Pollard and DeCanto's parameterization suggested, or it was partially suppressed by factors not represented in the model. The analysis did not eliminate MECI as a real process. It argued that its rate had been overestimated in the original parameterization. The current state of the MECI literature is genuinely contested in a way that MECI is not. MECI has observational support from multiple current retreating glaciers. MECI has theoretical support, some observational evidence from specific settings, including calving events at Jakobshavn and at Antarctica's Pine Island Glacier, and an unresolved calibration debate. The IPCC's sixth assessment report placed MECI in the low likelihood, high impact category, acknowledging its physical plausibility and potentially enormous consequence while not including it in the likely range of projections. For the purposes of this investigation's risk assessment, the honest framing is that MECI may or may not contribute substantially to 21st century Greenland mass loss. The zombie ice floor does not require it. MECI does not require it. The committed rise from documented, observationally supported processes is significant regardless of how the MECI debate resolves. But MECI represents the mechanism by which the ceiling of possible outcomes sits much higher than the ceiling defined by MECI alone, and that possibility is not scientifically excluded. The investigation has been building toward a direct confrontation with the actual quantities, not ranges, not scenarios, not model outputs qualified by confidence intervals, but the best current scientific assessment of what is already committed to the ocean, regardless of future human choices. Committed sea level rise, the rise physically unavoidable given the current state of the climate system even under immediate, complete emission cessation, has components from multiple sources. The Greenland zombie ice, 365 millimeters, as established by Box and colleagues, verified against accumulation area ratio measurements across the full ice sheet. The ocean thermal expansion commitment. The ocean has absorbed an enormous fraction of the excess heat generated by greenhouse gas emissions, and that heat will continue to drive thermal expansion even if atmospheric concentrations were held constant today. The IPCC's estimate of committed thermal expansion under a stable forcing scenario is approximately 100 to 200 millimeters over the coming decades to century. Mountain and ice cap glaciers worldwide, the Himalayas, the European Alps, the Andes, the Alaska Range, the Arctic ice caps are all in sustained negative mass balance and will contribute additional committed rise, estimated at roughly 100 to 150 millimeters from the most comprehensive glacier inventory analyses, including the work of Ben Marzayan at the University of Bremen, whose global glacier mass loss reconstructions have been a reference in this area. The Antarctic ice sheet's committed contribution is the most uncertain component of the total. The IPCC's sixth assessment report provided a likely range for Antarctic contribution to 2100 sea level of approximately 3 to 30 centimeters under intermediate emission scenarios, with tail risks substantially larger under high emissions if ice sheet dynamic processes operate as the models incorporating MESI suggest. The committed component of the Antarctic contribution, the rise from processes already in motion rather than future forcing, is harder to separate from the scenario-dependent component than for Greenland, because Antarctic mass loss is currently smaller, and the dynamic signals are concentrated in West Antarctica's marine basins, rather than distributed across the ice sheet as Greenland's zombie ice is. Add these components: Greenland zombie ice at 365 millimeters, thermal expansion commitment at 150 millimeters at the midpoint, mountain glacier commitment at 125 millimeters at the midpoint, and a conservative Antarctic committed contribution of perhaps 50 millimeters from ongoing dynamic processes. And the total committed global mean sea level rise already locked in is in the range of approximately 600 to 700 millimeters. 60 to 70 centimeters of unavoidable, committed, already decided sea level rise. 60 to 70 centimeters. That is a number that has not been communicated clearly to the coastal communities, the infrastructure planners, and the emergency managers who are making decisions today about long-lived investments that will have to operate in that sea level environment. The IPCC's projected likely range for 2100 sea level rise under intermediate emissions scenarios is approximately 32 to 62 centimeters, a range whose lower bound is below the committed rise calculation's lower bound, a discrepancy that reflects the difference between committed rise under instantaneous emission cessation and projected rise under continued but reduced emissions trajectories, as well as the genuine uncertainties in partitioning the Antarctic contribution. The planning implication is uncomfortable. Infrastructure designed to the lower end of current IPCC projections may already be undersized relative to the committed physics before a single additional ton of greenhouse gas is emitted. The Greenland story is not self-contained. It connects to the AMOC investigation this channel conducted in a previous episode through a physical chain that is as direct and well documented as any of the mechanisms we have examined in this script. It connects to the coastal storm risk story. It connects to the sea level anomaly dynamics of the eastern seaboard. These are not separate phenomena whose convergence is coincidental. They are coupled components of a single Earth system whose coupling is the central insight that the compound event framework repeatedly returns to. The connection begins with freshwater. Greenland's accelerating ice loss delivers 250 to 300 billion tons of freshwater into the North Atlantic annually. That freshwater enters the ocean in the regions, the Labrador Sea and the Nordic Seas south of Greenland, that are the primary deep water formation zones of the Atlantic meridional overturning circulation. Freshwater is less dense than saltwater. When it dilutes the surface salinity of these critical convection regions, it reduces the density of the surface water. The surface water becomes less inclined to sink. The convective overturn that drives the downwelling branch of AMOC weakens. The cold blob, the persistent negative sea surface temperature anomaly south of Greenland, documented in the AMOC investigation, intensifies. AMOC weakening, in turn, reduces the northward transport of warm water in the Gulf Stream system. That warm water, deprived of its northward export pathway, accumulates in the subtropical and western North Atlantic. Sea surface temperatures in the development zone for coastal storms along the eastern seaboard elevate. Sea surface height along the northeastern United States coast rises through the geostrophic adjustment mechanism. The storm surge baseline on which the next major coastal cyclone will operate is elevated above historical norms. Every link in this cascade has been independently documented. The Greenland freshwater AMOC link, established by GRACE FO mass loss data, Argo salinity observations, and the work of Penny Holliday at the National Oceanography Center, documenting progressive freshening of the upper Labrador Sea. The AMOC sea surface temperature link, established by the cold blob analysis and Western North Atlantic heat content data from Argo profiles. The sea surface temperature storm intensity link, established by Carrie Emanuel's potential intensity framework and the observational record of rapid intensification along the East Coast. The background sea level storm surge link, established by Radley Horton and colleagues' Sandy analysis, quantifying the contribution of pre-existing sea level anomalies to surge height at the battery. When this channel covers the next major coastal storm on the eastern seaboard, the Greenland mass loss rate from the previous year will be part of the risk context. When this channel returns to the AMOC investigation, the zombie ice commitment will be part of the forcing picture. The ice sheet, the ocean circulation, and the coastal storm system are not separate story threads. They are the same story told from different measurement platforms at different timescales toward the same conclusion. The North Atlantic system is changing coherently in a direction that systematically elevates the risk environment for every coastal population in its influence domain. The abstract language of sea level projections can create a protective distance from the human reality of what committed sea level rise means. This part of the investigation explicitly collapses that distance because the committed physics has specific addresses. Miami, Florida sits on Miami-Dade County's limestone karst geology, porous, permeable rock that cannot be sealed against sea level rise the way clay-based soils or solid granite can. When sea level rises, the water table beneath Miami rises with it, because the ocean and the freshwater aquifer are in hydraulic communication through the permeable limestone. Flood barriers constructed at the surface, the seawalls, the storm surge barriers, the levees provide no protection against a rising water table that seeps upward through the ground from below. This geological vulnerability was documented in detailed hydrology assessments by Harold Wanless at the University of Miami, whose work on South Florida's sea level exposure has been among the most comprehensive available. Miami sits at an average elevation of approximately 1.8 meters above current mean sea level. The committed zombie ice rise of 37 centimeters represents approximately 20% of that buffer before any additional warming is applied. Add the thermal expansion commitment, the mountain glacier contribution, and a conservative Antarctic dynamic component, and the committed rise approaches half of Miami's average freeboard, the vertical distance between current sea level and the land surface. That is the committed floor. The projections for 2100 under continued emissions trajectories substantially exceed it. Miami Beach, built on a narrow barrier island, averaging approximately 1.3 meters above sea level, is already experiencing regular tidal flooding events. Called sunny day flooding or nuisance flooding during king tides when no storm is present. The current king tide flooding frequency in Miami Beach has increased from roughly once per decade in the 1960s to multiple times per year in the 2010s and 2020s. The committed sea level rise will not reduce that frequency. It will make what is currently a nuisance event the permanent condition, and make what is currently a storm surge event a catastrophic inundation scenario. The low-lying delta regions of South and Southeast Asia face a compound vulnerability that combines committed sea level rise with land, subsidence from groundwater extraction, a combination that produces local relative sea level rise rates that substantially exceed the global mean. The Mekong Delta in Vietnam is sinking at rates of 1 to 3 centimeters per year in some measurement locations due to groundwater extraction and sediment starvation from upstream dams, while simultaneously experiencing the global mean sea level rise signal. The combination produces a rate of relative sea level rise that will outpace adaptation capacity in significant portions of the delta within decades. 17 million people live in the Mekong Delta. The delta produces approximately 50% of Vietnam's food supply. The rice paddies that cover the delta's surface are already experiencing saltwater intrusion. The advance of saline water into freshwater agricultural land. As rising sea levels and reduced upstream freshwater flow during dry seasons push the salt wedge further inland in the tidal channels. Saltwater intrusion reduces rice yields and, at sufficient concentrations, makes paddy agriculture impossible. The World Bank's assessment of Mekong Delta vulnerability estimated that without intervention, rising sea levels and salinity intrusion could displace approximately 1 to 2 million people from the delta by mid-century under moderate sea level rise scenarios. The committed sea level floor makes the moderate scenario the starting point, not the midpoint. The Nile Delta in Egypt, home to approximately 40 million people and producing a substantial fraction of Egypt's food supply on some of the most fertile agricultural land in the world, sits at an average elevation of approximately 1 to 1.5 meters above sea level across most of its cultivated area. The delta has been sinking due to the reduction of sediment supply from the Aswan High Dam, which traps the Nile's sediment load behind it rather than allowing it to replenish the delta surface. While sea levels rise, the committed rise from zombie ice alone will bring mean sea level to within the storm surge range of large portions of the delta's agricultural land. These are not hypothetical future populations. They are people currently alive on land that currently exists in communities that currently function. The committed physics is already decided. The question is whether the governance and economic systems managing their exposure will respond faster than the sea level rises. The committed sea level rise numbers, applied to the global coastal population distribution, produce a migration arithmetic that has no precedent in the documented history of human civilization. This is not rhetorical hyperbole. It is a calculation. The current global coastal population within 10 meters of sea level elevation is approximately 1 billion people, distributed across every inhabited continent. The distribution is not uniform. It is concentrated in the large river delta regions of South and Southeast Asia, in the Pacific island nations where no high ground exists, in the low-lying coastal nations of West Africa, and in the developed coastal cities of Europe and North America, whose historical economic prosperity was built on maritime trade access. The World Bank's Groundswell report projected 216 million internal climate migrants by 2050 under a scenario that incorporated moderate sea level rise, not the committed floor we have established in this investigation, but a moderate projection that sits below the committed rise. The sea level contribution to that migration figure was concentrated in 3 regions: South Asia, Sub-Saharan Africa, and East Asia, and the Pacific. Bangladesh alone was projected to generate 13 million internal climate migrants by 2050 from sea level rise, salinity intrusion, and intensified flooding. 13 million people moving within Bangladesh. Bangladesh is a country of approximately 170 million people, in an area roughly the size of the state of Iowa. It is already one of the most densely populated countries on Earth. The infrastructure, economic capacity, and social systems required to absorb 13 million additional internal migrants from the coastal districts have not been built. They are not currently being built at a pace consistent with the timeline that the committed sea level projections imply. The international migration component, the movement of people across national borders driven by sea level rise and its consequences, is not included in the World Bank's Groundswell figures, and is substantially harder to project because it depends on political decisions, legal frameworks, and bilateral agreements that do not currently exist in the form the numbers require. The Pacific Island nations, Kiribati, The Marshall Islands, Tuvalu, the Maldives are among the most directly threatened. Their governments have been pursuing international agreements on climate migration rights and land access in other countries, with limited success to date in securing binding commitments from larger nations. Robert McLeeman at Wilfrid Laurier University, who has studied climate migration from both historical and contemporary perspectives, has pointed out that every major historical migration event of comparable or smaller scale, the Dust Bowl migration of the 1930s involving approximately 2.5 million people over a decade, the partition of British India in 1947, displacing approximately 14 million people over months, the Syrian refugee crisis beginning in 2011, displacing approximately 6 million people internationally, produced severe social stress in both origin and destination communities, despite occurring under conditions where the total numbers, the speed of movement, or both were smaller than the committed sea level scenario implies. The governance systems that exist for managing international migration, the 1951 Refugee Convention and its 1967 Protocol, the international frameworks for managed migration operated through the International Organization for Migration, were designed for political refugees and economic migrants. They were not designed for the managed, multi-decade, multi-hundred million person relocation that committed sea level rise implies for low-lying delta regions and Pacific island nations. The legal category of climate refugee does not exist in binding international law. The infrastructure to accommodate it does not exist. Neither is being built at the necessary scale. The ice sheet modeling community occupies an unusual and uncomfortable position in the context of this investigation. The physical processes driving Greenland mass loss, basal melt, marine instability, zombie ice disconnection, subglacial hydrology are understood at the process level with increasing confidence from field and remote sensing observations. The numerical representations of these processes in the computational ice sheet models that produce the quantitative projections used in IPCC assessments are still insufficiently developed in several critical respects. The result is a situation where the observational evidence is more alarming than the model projections, because the models are not yet capturing all of the observed behavior. This statement, that the real ice sheet is doing more than the models project, is not speculation. It is documented. The MBA synthesis of satellite observations has consistently found that actual Greenland mass loss falls at or above the upper end of the IPCC's projected likely range for the corresponding period. When comparisons are made, the models were calibrated on historical observations. As the ice sheet accelerates into a regime that has no historical analog in the period of direct observation, the models extrapolate from a calibration that no longer represents the physical state. The primary modeling uncertainties center on three processes. First, the representation of ocean-ice interaction at glacier fronts. The submarine melt and calving dynamics that Rignot's submarine melt reassessment revised upward by factors of 7 to 8. Current ice sheet models use simplified parameterizations of submarine melt that do not fully represent the turbulent mixing and density-driven circulation that oceanographic observations show is controlling the actual melt rates. Second, the representation of subglacial hydrology, the distributed versus channelized drainage dynamics that control basal sliding velocity. Ice sheet models have made substantial progress in including hydrology, but still do not represent the full complexity of subglacial water routing under the observed meltwater forcing. Third, the fracture mechanics of ice cliff failure, the MICE process whose quantitative behavior remains debated and whose parameterization is not yet constrained from first principles. Robert Kopp at Rutgers University, whose probabilistic sea level projection framework has become a reference in the field and has been incorporated into federal planning guidance, has developed methods for quantifying and communicating the asymmetric uncertainty structure of ice sheet projections. His framework makes explicit what standard projection ranges can obscure. The probability distribution of sea level rise outcomes is not symmetric around the central estimate. The tail toward higher outcomes is fatter than the tail toward lower outcomes, because the physical processes that produce higher outcomes, dynamic ice loss, marine instability, are the same processes that models underrepresent. Tail risk is the relevant planning metric for infrastructure with long design lives and high failure costs. For coastal infrastructure, the relevant question is not the median projected sea level. It is the level below which sea level will remain with high 90 or 95% confidence. That level, computed from the asymmetric probability distributions that COPS framework produces, is substantially higher than the median. The institutions using sea level projections for planning purposes, the Army Corps of Engineers, FEMA, the Dutch Delta Program, national coastal adaptation bodies, are beginning to grapple with this asymmetry. The transition from central estimate planning to tail risk planning is not complete and is not proceeding uniformly across jurisdictions. It is, however, the direction that the science is pushing the practice, and it is the direction that the committed physics of Greenland's zombie ice makes urgent. The scientific record on Greenland ice loss, committed sea level rise, and the physical processes that determine the ceiling above the zombie ice floor is published, peer-reviewed, and publicly available. The gap between what that record establishes and what institutional governance has translated it into is, in the terms of this investigation, the most operationally consequential finding. The IPCC synthesizes this science and communicates it to policymakers through the Summary for Policymakers documents that represent the consensus of the world's governments. The Summary for Policymakers for the 6th Assessment Reports Working Group. One contribution on the physical science basis stated explicitly that global mean sea level rise is accelerating, that ice sheet contributions are increasing, that committed rise from current warming is substantial, and that the high-end scenarios, driven by ice sheet dynamic processes, cannot be excluded from risk assessments. Every government that participated in the IPCC process received this communication. The Army Corps of Engineers Sea Level Rise Guidance, Engineering Circular 1110-2-8282, updated in 2019, provides 3 scenarios for project planning: low, intermediate, and high, based on NOAA's technical report on global and regional sea level rise scenarios. The high scenario accounts for potential ice sheet dynamic contributions and produces the kind of planning numbers that the zombie ice research suggests are minimum commitments. The guidance is available. Whether it is applied depends on project-specific cost-benefit analyses, congressional appropriations for hardening investments, and the willingness of project sponsors to design to the high scenario when the intermediate scenario is cheaper to build to. The political economy of coastal adaptation investment systematically discounts the tail risk. Infrastructure investment decisions are made by elected officials on political cycles of 2 to 6 years. The sea level rise risk manifests on timescales of decades. The cost of over-designing, building to a higher sea level scenario than ultimately occurs, is immediate and certain. The cost of under-designing, building to a lower scenario that the committed physics will exceed, is deferred and uncertain in timing. Political systems tend to incur immediate certain costs only when immediate certain consequences motivate them. The consequences of under-designed coastal infrastructure manifest gradually through increasing flood frequency and storm damage until a catastrophic event concentrates attention. By then, the infrastructure that needed to be built differently has already been built. The Netherlands has broken this political economy to a greater degree than any other nation. Through a combination of existential historical motivation, the 1953 North Sea flood killed approximately 1,800 people and inundated a significant fraction of Dutch territory, producing a political mandate for the Delta Works flood defense system, and an institutional structure that insulates long-term coastal defense investment from short-term political cycles. The Delta program, established in 2010, commits to continuous reassessment of sea level rise projections and continuous updating of flood defense standards and investment schedules. It is explicitly designed to avoid the political economy trap. The Netherlands' approach is instructive and is referenced in coastal adaptation literature globally. It is also the product of specific historical trauma and institutional arrangements that have taken decades to develop and that are not easily transferable to the governance systems of Bangladesh, Vietnam, Egypt, or the Pacific Island nations that face the most acute exposure to committed sea level rise. The adaptation investment gap between what the zombie ice commitment requires and what the most exposed nations can finance is structural. It is not a problem that can be solved by the affected nations alone, and the international financial frameworks for climate adaptation financing, the Green Climate Fund, the Loss and Damage Fund established at COP27 in 2022, are capitalized at fractions of what the committed sea level rise implies will be needed. Every investigation of this kind arrives at the moment where the evidence must be organized into the honestly competing interpretations that the data supports. Not a single conclusion. The data does not support a single conclusion with sufficient confidence to present it that way. Three genuinely different readings of what the committed physics of Greenland's zombie ice means for the coming century of coastal civilization. The first interpretation is the one embedded in current institutional planning frameworks and reflected in the central estimates of the IPCC's sixth assessment report. In this reading, the zombie ice commitment of 365 millimeters from Greenland, combined with committed thermal expansion and mountain glacier contributions, represents a manageable adaptation challenge that manifests gradually over the course of the century and beyond. The marine instability processes underway at Jakobshavn and other outlet glaciers are real, but operate on timescales long enough that governance systems have decades to develop adaptation frameworks, coastal infrastructure can be hardened, or communities can be managed in retreat, and the migration produced by committed sea level rise, while large, takes place over sufficiently long time frames for social and political systems to accommodate it with significant stress, but without systemic failure. In this interpretation, the scientific understanding of the committed risk is sufficient to motivate the necessary investment if political will exists. The Netherlands provides the model. The challenge is replicating that model's institutional and financial depth across the full range of exposed nations. In this reading, the committed sea level rise is a severe and expensive problem. It is not an unmanageable one. This interpretation is supported by the historical resilience of human societies to environmental change, by the continued development of coastal engineering and adaptation tools, and by the observation that the communities most exposed, the Mekong Delta, the Nile Delta, coastal Bangladesh, have been managing flooding and sea level variability through traditional adaptive practices for generations. It assumes that the political and financial systems required for adaptation at scale can be built in time. That assumption is the critical uncertainty it rests on. The second interpretation is the middle position that the weight of evidence assembled in this investigation supports. In this reading, the zombie ice floor of 365 millimeters is not the number that will be tested by 21st century infrastructure, because the marine instability processes that are already observationally documented, Jakobshavn's retreating grounding line, the revised submarine melt rates from Rignow's analysis, the accelerating dynamic component of the GRACE-FO mass loss signal, will produce committed contributions substantially above the zombie ice floor within the infrastructure's design lifetime. In this reading, the relevant committed rise number for 21st century coastal planning is in the range of 1 to 1.5 meters from all sources combined, with the actual rise potentially exceeding this range if the dynamic processes accelerate at the rates suggested by the most recent observational data. The infrastructure currently being built to IPCC central estimates is being built to a standard that the committed physics will exceed within its design life. The adaptation investment gap is not a future problem to be solved by future generations. It is a current problem that is being deferred at the cost of locked-in future vulnerability. In this interpretation, the migration that committed sea level rise will produce is not a decades-long managed transition that existing institutional frameworks can accommodate. It is a process that will overwhelm those frameworks in the most exposed regions within the planning horizons of current coastal infrastructure investments. The governance response required is not incremental adjustment to existing coastal planning guidance. It is a fundamental restructuring of how exposed nations and communities are supported to relocate financially, legally, politically, and logistically before the committed sea level makes the existing coastal geography uninhabitable rather than merely increasingly costly to defend. The third interpretation is the one that the physics does not exclude, and that the paleoclimate record has precedence for, though not in any time period that human civilization has experienced. In this reading, the combination of marine instability processes at Greenland's retrograde sloped glacier margins, potentially combined with ice cliff instability mechanics, is not operating on the multi-decadal timescale that the IPCC's Central Estimates project. The system is in the early stages of self-reinforcing retreat that, once fully underway, operates at rates comparable to the geological evidence from past warm periods, rates that produced meters of sea level rise per century in past glacial terminations and interglacial warming events. In this reading, the tipping point question is not open. It has been answered by the observational trajectory of the past 3 decades, a consistent acceleration of mass loss, a consistent expansion of the dynamic component, a consistent retreat of grounding lines on retrograde sloped beds. And the answer is that the ice sheet has already crossed into the regime where committed loss substantially exceeds the zombie ice calculation. The ceiling is not 1 meter. It is multiple meters within this century, manifesting not at the end of the century, under the worst-case scenario, but at the middle of the century, under the process dynamics currently observable. Only the continued evolution of the GRACE-FO, Cryosat-2, and INSAR observational record will tell us which interpretation is correct. The data will resolve the open questions. The question that this investigation poses directly to the governance systems of coastal civilization is whether the response is calibrated to wait for that resolution, or whether the asymmetric uncertainty, the fat right tail, the skew toward higher outcomes, the systematic underperformance of models relative to observations, justifies action at the scale that the second or third interpretation demands before the first interpretation's comfortable timeline has been definitively excluded. Strip it down to what the evidence actually says, in the plainest terms the science supports. What is confirmed? The Greenland ice sheet is losing mass at an accelerating rate, documented consistently and independently by GRACE-FO, Cryosat-2, and INSAR velocity measurements over periods of decades. The mass loss rate has increased approximately 8-fold, from the 1990s to the most recent measurement decade. The zombie ice commitment of a minimum of 365 millimeters of global sea level rise equivalent is published, peer-reviewed, and has not been successfully contested in the scientific literature. Submarine basal melt rates at Greenland's glacier fronts have been revised upward by factors of 7 to 8 based on oceanographic measurement, a revision that fundamentally changes the ice sheet's modeled sensitivity to ocean warming. Marine ice sheet instability dynamics are observationally documented at Jakobshavn Isbro, and consistent with the retrograde bed geometry mapped by the BedMap Greenland compilation. What is confirmed about the coupling? The Greenland freshwater flux to the North Atlantic is the primary documented driver of the long-term AMOC weakening signal identified in the cold blob thermal anomaly and the rapid array measurements. AMOC weakening drives elevated western North Atlantic sea surface temperatures and regional sea level rise along the northeastern United States coast through the mechanisms established in the AMOC investigation. The compound risk from this coupling, elevated coastal storm intensity fueled by anomalous sea surface temperatures, arriving at a coast with a reduced storm surge buffer from elevated background sea level, is not a modeled projection. It is the current observational state of the North Atlantic. What is genuinely uncertain, the rate at which marine instability dynamics will accelerate mass loss beyond the zombie ice floor commitment, whether the global temperature trajectory of 2023 and 2024, which transiently approached the 1.5 degrees Celsius threshold, identified as Greenland's potential tipping point, represents a durable crossing of that threshold or a temporary exceedance from which the system can recover. The MICE contribution to 21st century mass loss, physically plausible, observationally partially supported, quantitatively debated, and potentially enormous if the mechanism operates as theorized. What is unknown, whether the institutional frameworks governing coastal adaptation investment and climate migration management will be reformed at a pace consistent with the committed sea level timeline. Whether the asymmetric uncertainty in ice sheet projections will be incorporated into planning standards before the committed sea level rise makes the under-designed infrastructure vulnerable. Whether the international financial frameworks for climate adaptation will be capitalized at the scale that the migration arithmetic implies. The researchers whose work this investigation has drawn upon are not alarmists. They are empiricists. They follow data, the specific character of the concern that runs through their published work, rarely stated as alarm, in the restrained language of peer review, but audible in the precision with which they quantify risks and in the frequency with which they engage with governance and policy audiences, reflects a community that understands what its measurements imply and is trying to ensure that understanding reaches the decision-making systems that can act on it. Jason Box has been one of the more publicly engaged scientists in this space, combining his work at GEOS, where he leads an ice and climate research group conducting field campaigns on the Greenland ice sheet every summer, with direct public communication through interviews, articles, and social media presence that translates the technical findings into language accessible to non-specialist audiences. His zombie ice calculation was published in a peer-reviewed journal, but was also communicated in public forums in language chosen to convey the commitment and irreversibility of the finding without the hedging that journal language requires. Box has stated publicly and directly that the gap between what the ice sheet data shows and what the societal response reflects is the most alarming aspect of the situation. Not the ice loss itself, but the failure to respond to it at the scale its implications demand. Eric Rigneau, whose submarine melt reassessment at JPL fundamentally revised the ice sheet community's understanding of ocean ice interaction rates, has been similarly direct in public communications about the implications of the observations. In interviews following the 2019 Science publication, he emphasized that the revision of submarine melt rates upward by a factor of 7 to 8 was not a marginal correction to previous understanding, but a fundamental change in the quantitative framework for assessing how fast the ice sheet can respond to ocean warming. That change propagates through every model calibrated on the previous estimates. Fiamma Stranio's ocean fieldwork in Greenland's fjords, deployments in some of the most logistically challenging oceanic environments accessible to research, has produced the direct observational evidence of Atlantic water temperatures at glacier fronts that motivates the ocean-ice interaction research across the field. Her work is the observational anchor for the temperature forcing that drives the submarine melt that Rigneau quantified, and that the ice sheet models are still working to represent accurately. Jonathan Bamber's expert elicitation work, synthesizing the structured judgment of the ice sheet science community on probability distributions for sea level contributions, was motivated by a recognition that model-based projections alone were failing to capture the full range of physically plausible outcomes, because the models were not representing all relevant processes. The expert elicitation approach asks the scientists who best understand the physics, not the models, what probability they assign to various outcomes. The results consistently produce fatter tails toward high sea level contributions than the model ensembles alone suggest. Robert Kopp's probabilistic framework development is a direct response to the communication challenge: how to convey asymmetric, fat-tailed uncertainty to decision makers who are accustomed to receiving central estimates with symmetric uncertainty ranges. His frameworks have influenced federal planning guidance and IPCC methodology. The translation from scientific probability distribution to planning standard is still incomplete. The gap between what COPS distributions say and what the Army Corps guidance requires is real, but the intellectual tools for bridging it exist. The community is communicating. The translation loss between what these scientists are saying and what the planning frameworks are using is the operational gap that has characterized the relationship between climate risk science and infrastructure governance for decades, and that the committed physics of Greenland's zombie ice is making progressively less tolerable as the sea level floor rises toward the design parameters of current coastal infrastructure. At the end of this investigation, the evidence leads somewhere that deserves to be stated without qualification. The Greenland ice sheet accumulated over approximately 100,000 years through the steady, patient deposition of snowfall on its central dome. The compression of that snow into ice, the slow gravitational flow of that ice toward the margins, and the dynamic balance between accumulation and calving that maintain the ice sheet in a state of approximate mass equilibrium through multiple millennia of climate variability. That equilibrium, which supported sea levels at or near their current position during the Holocene period of relative climate stability that made agricultural civilization possible, is over. It ended sometime in the late 20th century when the imbalance between accumulation and ablation crossed from negligible to measurable to accelerating. The 365 millimeters of committed zombie ice rise is the accounting statement of that ended equilibrium. It is the minimum balance owed to the ocean by the ice that has already been cut off from its replenishment. It will be paid. The physics has decided this. The question of when and through what dynamic path is open. The question of whether it occurs is not. The marine instability dynamics documented at Jakobshavn and visible in the accelerating dynamic component of the Grace FO mass law signal add terms to the committed balance whose full magnitude the models have not yet resolved. The submarine melt revision of Rignot and colleagues adds acceleration to the timeline. The subglacial hydrology changes and the Atlantic water warming add continuous forcing to the processes that were already underway. The primary open loop of this investigation has a floor and a rising ceiling and a timeline that is measured in decades for the floor and centuries for the ceiling. But decades are the planning horizon of the coastal infrastructure being built today. The floor alone, 37 centimeters of committed zombie ice rise, will interact with every tide, every storm, every surge along every coast on Earth for as long as those coasts exist. The ceiling, whatever the marine instability dynamics ultimately contribute above the floor, will continue to rise as the observational record accumulates data and the modeling community develops better representations of the processes driving the acceleration, the gap between what the science has established and what the planning frameworks are using, the gap between the committed migration arithmetic and the governance frameworks that exist to manage it, the gap between the published risk and the investment response. These are the operational dimensions of a physical commitment that the ice sheet's own measurements have been recording for 3 decades, in data that streams continuously from 3 satellite systems and thousands of oceanographic sensors toward the same conclusion from independent directions. This community watches because the gap between what the evidence shows and what the institutional response reflects is where the most consequential stories live. We will be tracking the Grace FO monthly mass anomaly numbers. We will be here when new grounding line retreat data or submarine melt reassessments demand examination. We will bring you the cryosat surface elevation records, the Argo fjord temperature profiles, the INSAR velocity updates, and the honest, unhedged statement of what each of them means every time. Because the question of what Greenland is doing, measured in billions of tons of ice per year, flowing into an ocean that has nowhere to put it except against every coast on Earth, is the heaviest and longest and most irreversible story this investigation has ever tracked. The ice remembers 100,000 years of accumulation. It is forgetting, now, faster than it ever has. And the water that was that ice is coming for every coastline that was built on the assumption that the ice would stay. We will be watching. We will be here.